Imagine just for a second a universe that's literally built out of pure mathematics. No physical matter, no physics, just this sprawling, infinite digital grid stretching out in every direction. Well, today in this explainer, we're going to explore the architecture of that abstract reality by stepping into the world of differential geometry. It's an area that holds some of the absolute most beautiful results in all of math, basically using the tools of calculus to understand the very fabric of curves and surfaces. It's kind of like putting on a pair of conceptual sci-fi glasses that let us see the hidden scaffolding of everything around us. But before we start building up this mathematical universe, I want you to think about a really fundamental mystery. How do you measure a world that you can't actually see from the outside? Like, if you're entirely trapped inside a specific space, bound to its dimensions, and you literally can't step out to look down at it, how do you even know what shape your universe actually is? I want you to keep that question right in the back of your mind because it's exactly where we're heading today.
So, to figure that out, here is the roadmap for our explainer. First, from curves to space. Second, defining a surface. Third, a gallery of surfaces. Fourth, the art of revolution. And finally, measuring the mathematical world. Okay, let's dive right into part one. From curves to space, the first dimension. Now, when I say the word curve, your mind probably jumps straight to a line drawn on a piece of paper, maybe a parabola or just a simple circle. But in differential geometry, a curve is way more dynamic than that. Mathematically speaking, it can actually be defined in two totally distinct ways. It can be viewed as the exact path traced out by a moving point over time, or it can be looked at as a set of static points that all satisfy a specific condition, basically reaching a certain mathematical level. And honestly, looking at these two concepts side by side brilliantly illustrates the difference. First, you've got level curves. Think of the classic equation of a circle, x squared plus y squared equals 1. This is a static set of points, every coordinate x and y where that mathematical quantity hits the exact level of 1. But then, on the flip side, we have parametrized curves, which we denote as gamma of t. With this one, imagine a point actually moving through our grid over a scalar parameter t, which you can just think of as time. If gamma of t is the position of the point at time t, then the curve is the actual cinematic path it's tracing through space. In differential geometry, we are constantly shifting gears between these static equations and these dynamic moving paths.
All right, moving on to part two, defining a surface, breaking into 3D.
So how exactly do we mathematically define a surface once we're working in 3D space? Well, the definition here is just incredibly elegant. Basically, a surface is a subset of 3D space that looks exactly like a piece of a flat 2D plane if you zoom in close enough to any given point. I think the best metaphor for this is actually the Earth itself. From outer space, right, it's this massive, complex sphere. But to an observer standing right there on the ground who only sees out to the horizon, the surface appears to be a perfectly flat plane. Mathematically, a surface has to behave in this exact same way. If you zoom in infinitely close to any point, the complex geometry just flattens right out.
With that rule in place, we can start generating the fundamental building blocks of our mathematical universe. We've got planes, which are essentially your flat grids. We've got spheres, which are defined as all the points sitting a constant distance away from a central point. Then there are cylinders, created by parallel vertical lines, and cones, formed by lines radiating out from a single vertex. Oh, and level surfaces. These are basically the 3D equivalents of those static equations we were talking about just a minute ago, where a function of x, y, and z reaches a constant level. These are the core geometric assets populating our abstract 3D space.
Next up, part 3, a gallery of surfaces, the art of revolution.
You know, we can actually construct some highly complex, beautiful 3D shapes simply by manipulating 1D curves through this amazing process called creating a surface of revolution. And the algorithm for this is beautifully simple. Step 1, you just take a flat 2D profile curve. Step 2, you pick a straight axis line, let's say the z-axis on our digital grid. And step 3, you just sweep or rotate that 2D curve in a full circle right around the axis. Literally, just by spinning a line, you end up carving out an entire 3-dimensional surface.
And when we really push this process to its absolute limits, we get these stunning conceptual structures. Take a catenoid, for example, a highly complex surface of revolution. It almost looks like some sci-fi wormhole connecting 2 different planes of existence, right? But it's actually generated using that exact same simple rule. You take a specific curve, in this case a catenary curve, and you sweep it around an axis. That whole mind-bending geometry is, when you get right down to it, really just the ghost of a spinning line.
All right, moving into part 4, measuring the mathematical world, the inside view. Up until now, we've spent all this time looking at these structures from the outside, basically playing God in our 3D mathematical universe. But now, it's time to completely shift our perspective and come right back to that hook we started with. I absolutely love this thought experiment from the source material. Imagine a geometrically inclined bug living its entire life on one of these surfaces. Now, this bug has no concept of 3D space. It has no idea it's living on a sphere or a catenoid. To this bug, its surface is the entire universe. The very first thing this bug is going to want to do is figure out how to measure the distance between 2 points. But taking a straight line through 3D space just isn't an option. That would mean digging through the surface or flying above it, which the bug obviously can't do. It has to measure distance by actually walking along the curve of the surface itself.
So the really crucial question is, how does it actually make that measurement? Well, in differential geometry, we use this incredible tool called the first fundamental form. This is the mathematical framework that lets our bug compute lengths, angles, and areas directly on the surface. It uses the coordinates of the surface to measure distance intrinsically, meaning it never even has to reference that massive 3D void outside of it.
But you know, differential geometry gives us an even deeper level of understanding than that. Because while the first fundamental form is what our bug uses to measure the length of, say, its daily commute, there's also the second fundamental form. This tool measures the actual bending and curvature of the surface into the ambient 3D space. It basically measures how the bug's universe folds and arcs all around it, quantifying the invisible shape of reality using complex matrices and tangent planes. It is literally measuring the shape of space itself.
Which brings us to our final thought for this explainer. When we look at curves, surfaces, and the massive abstract grids of differential geometry, we're really forced to ask, are the rules of geometry dictated by the space you occupy, or the perspective from which you measure it? Because, as we've seen, a line can be a static equation or a moving point. A surface can be a flat plane up close or a complex sphere from afar. The math stays exactly the same, but the reality changes depending entirely on where you stand. Thank you so much for joining me on this dimensional awakening. Keep questioning your coordinates and keep learning.